slide, and what it shows is an image from a crawling mouse cell. So down here, where the different components of interest have been stained. So down here you see this blue part, which is the nucleus. You see the red part here, which is the dyed actin filament, which encloses the body of the cell and extends into these protrusions, which are responsible for the crawling of the cell. And you can see that if you look at one of these extensions, that you see these striated structures here, which suggests that the actin filaments, as the name also suggests, have a kind of directional order. And there is some energy being infused into the system through these myosin motors, which are here in green. They consume ATP, and this energy is then transformed into a tension that is conveyed to the network and provides the force which the cell needs to move. So from a fluid mechanical or from a continuum mechanical point of view, this is a beautiful but complicated problem where you have a continuum material, a complicated continuum material with directional order. You have an energy source which provides a tension, and you've got at least two interfaces at the substrate and even a free interface at the top. So wouldn't it be nice to have a continuum mechanical description for this that might tell us something about the biology eventually, but also give us some interesting things to play with, in particular also due to the coupling with the free interfaces. Now, the idea of associating the directional order in these filaments with liquid crystals was taken up by a group of researchers a while ago, and they basically used the Leslie-Erickson-Parodi theory for liquid crystals, which encodes the directional order in terms of a director field and included an active term. And one thing that they found out in a different paper with their theory is that that you can have a spontaneous flow transition. So if you think of a layer of this polar gel, as it is called, then depending on a critical thickness, you might have below the thickness a situation where the gel is stagnant. But if you exceed the critical thickness, you get a spontaneous flow transition, which might be related to some of the properties you see in the cell. Another thing that is very typical for even passive liquid crystals is the occurrence of defects. And this is, of course, exacerbated if you have a non-equilibrium system where additional energy comes into play. So you can have these structures, for example, like vortices or spirals or asters, and some of these have been seen in experiments with actin filament networks, in particular when you have a medium range of activity. So for low ranges of activity, you have a passive liquid crystal where defects tend to annihilate themselves. And for very high levels, which are not shown in this diagram here, you get again a homogeneous distribution. But for medium levels, you can get these structures. So here you see, for example, some of these aster-like structures. Now, how does the liquid crystal theory work? Well, it is, we've seen some of this before in previous talks. It is built around the free energy over here, which penalizes inhomogeneities, non-uniformities in the director field. In the full-fledged theory, you would have three elastic constants for the twist, display, and the bending. But here we've just collapsed everything into one contribution by choosing one constant for all of them. This is then incorporated into three balances: mass balance for an incompressible fluid, the balance for the tensions, and then of course the balance for the angular momentum. The HI here is the molecular field, which is just the first variation of the Osin-Frank energy, and you then have the total stress tensor, which enters the stress balance. It has the Newtonian terms over here, the Ericsson term, which depends on the free energy, and then you have these couplings with the motion of the molecular field. Now, this theory is the passive part of the theory, the one you use in liquid crystals. The active terms are encoded in these two terms over here. So one contributes to the angular momentum, and the other creates the stress in the network. Both of them are proportional to delta chi, which encodes the rate at which the ATP is hydrolyzed and produces energy. So the Leslie-Erickson-Parodi theory can to some degree also incorporate defects, point defects, but it is quite deficient in that respect, and in particular it has a tendency to create infinite energy at these defects. So extensions of the theory have been devised. One by Erickson incorporates an additional order parameter. So if Q is constant and non-zero, then you have basically the property of crystallinity, but at Q equals 0 you suppress the term, and by this regularize effectively the contribution to the infinite energy contribution to the free energy. And you can go beyond this and preserve, if you want, the head-tail symmetry by using Q tensors, which also have appeared in several talks and were pioneered, I think, by Dijen. And this can in turn be extended into a full-fledged hydrodynamic theory, which was done by Beris and Edwards using the Poisson bracket formulation. So then the Q tensor, the directional information, is then coupled back to the Stokes equation, essentially. So both theories, or both types of theories, can be extended into an active theory. I've already shown you the active version of the Leslie-Erickson-Parodi theory, and roughly at the same time, theories which extend the Beris-Edwards theory were also devised. Now, the Beris-Edwards theory is the one I want to focus here on, and there has been quite a bit of preliminary work on this one, mostly numerical work in 2D using hybrid lattice Boltzmann simulations. And what is interesting here is that while you do observe some of the phenomena you also see in Leslie-Erickson, the spontaneous flow transition, for example, they seem to be different, both in particular also in their symmetry properties. So there's a difference between these two theories. Other people have looked at higher order topological defects all in 2D or on spherical shells. Now, how is this theory constructed? Well, you need the Q tensors, which are essentially symmetric traceless matrices. And in 2D, they can be represented in this form. So you can reconnect with the director field here, and then you have this order parameter Q, which is 0 when you're in regions where singularities occur. So associated with this is a free energy, not the Oseen-Frank free energy, but the Landau-Dijen free energy. It has a contribution which penalizes non-uniformities in the director information. Over here, the elastic constant is called L1, and again, there are in fact normally several elastic constants which all have been collapsed into one for simplicity. And this double well potential over here effectively controls the order parameters, so it stabilizes constant non-zero values. We build this now into a dynamic theory, which is the active version of the Beris-Edwards theory. So we have the dynamic equation for the Q tensor with the molecular field H, which is again associated with the first variation of the free energy, the rotational diffusivity here, the coupling with the strain rate of the flow, and the active term. So psi is another parameter which turns up here and can be used to control the ratio between tumbling and aligning. The other two balance equations are the mass conservation for an incompressible fluid and the stress balance. Again, you have Newtonian terms, you have an active term, and you have these terms over here which are specific to the liquid crystal theory and couple the flow field to the molecular field. The geometry of the problem is highly dominated by interfaces, so you have to worry about those. And of course, if you think of a cell, the area at the substrate is rather complicated, but we will do something very simple here to begin with. So we just assume that there is a no-slip condition at the substrate, and we prescribe the direction of the director field, so we use strong anchoring. At the free surface, we have a kinematic condition, strong anchoring, and we just assume that there is a constant surface tension along the interface. Now we want to develop this into a theory where we simplify these rather complicated equations and take advantage in particular of the slender body ratio. So we introduce scalings to identify which terms are more or less important. So as is usual in lubrication theory, we introduce two scalings for the normal and the lateral length scale, and similarly two scalings for the two velocity components with a ratio epsilon. The ratio is effectively determined by the balance in the of the viscous stresses and the pressure scale. So this gives you this balance over here, and the pressure itself we assume is determined by the curvature of the interface. And this gives you a value for the small parameter which is associated with the capillary number, and we assume this one is small. So for liquid crystals, this has been pursued by a small but active group. For passive liquid crystals, and Ben Amar is, I think, sitting in the audience, maybe not right now, but in previous days. And then we have, so this is for different limits, and then we also have some work, but with other terms than in my situation, and with the Leslie Erickson Parodi theory, going back to a team of co-workers of Ramaswamy. So to get the richest possible model in this situation, and in particular include the energy supplying terms, we have to make some additional assumptions. The first assumption is that we have weak elasticity, so the Erickson number is small, and and for the active terms, we assume that one or ideally both of them give an order 1 contribution. So if we include this, do pages of algebra, which I'm not going to show for obvious reasons, we get this lubrication model here, which still is quite complicated. So you can imagine the work it takes to crank through all the algebra. Let me take you through the mechanics of this model. Down here you have the coupling of the free interface with the lateral flow field, which induces a cross-sectional flow, and the divergence of this flow simply determines via mass conservation how the surface evolves. Now what you need to know is V1, the lateral flow field, and this comes from this system of equations. So at each point you can determine the curvature, which determines this coefficient, and then you have to determine these other values by solving a boundary value problem. So here you have an ODE in the x3 direction for the order parameter, for theta, which is the angular direction of the director field, and here you have the expression for the velocity. And then you plug this back in and you get an evolution for eta. So this is a kind of a minimal model, even if it doesn't look very simple or minimal, to capture some of the physics happening in this biological setting. There are, of course, many other things that we could and should include. Here are 3 of them. So first of all, the actin density, as you might have seen from the initial picture, is not usually constant, and there's a background solvent, so you need to have additional density fields for these. Then we have completely neglected chemical reactions which drive a lot of the motion through polymerization and depolymerization of the actin filaments. And then we have the leading edge of the film, where quite a bit of the biology happens, but which is also interesting from a fluid mechanical point of view, because it's effectively a moving contact line, and you have the fluid mechanics plus the continuum mechanics coming from the liquid crystals, which both combine to produce a difficult situation there. Thank you very much for your attention.
A question or two? So do you intend to look at interfacial instabilities in this? Is that put on to imagine that?
Well,
I'm thinking of a little bit like Healy-Shaw somehow, where I have an active material.
yes, I mean, you could probably think of allopodia which have contact lines and where you have instabilities. And I know that Ramaswamy have looked at an instability, but they use an extra term which I don't quite understand. So that's certainly interesting.
Thank you. Thank our speaker again.